This section is on critical paths. Looking back on the decreasing time algorithm from the last section, we pretty much wanted to start the longer tasks first because they take the most amount of time. So here's an example of where a schedule could come out of that idea. This section is somewhat related to that, but we're going to treat things a little differently. So for any given vertex x of the diagraph, the critical path for x is the path from x, that vertex, to the end with the longest processing time total. Okay? And the processing time of a path, so multiple vertices, is defined to be the sum of processing times of all the vertices in the path. And so when we add the processing times of all the tasks along the critical path, we get what's called the critical time for task X. And always the critical time for the ending point should be 0. After finding all the critical times, the path with the longest processing time from start to end is called the critical path for the project, and the total processing time for that path is going to be called the critical time. So here's the same example we've used in the last couple of sections. We need to find the critical path, and to do that we have to find the critical times for each one of the vertices, and the next couple slides are going to show us the steps for doing that. So step 1, we're going to find the critical time for every vertex of the project diagraph. So we start at the end point and we work our way backwards towards the starting point according to this rule. The critical time for x equals the processing time of that vertex plus the largest critical time among the vertices incident from x. And I know that's a lot to kind of take in all at once. It'll make much more sense when we do an example. To elaborate on that one rule, the general idea is in this picture above. So if I've got task X that's pointing to three different vertices. Now remember, we're working backwards here. So if start was over here, we would have made our way this way and trying to figure out the critical time for this task X. Well, if this happens to have this task already happens to have the largest critical time, we're going to use this task's critical time and add it to the processing time for X. And generally we're going to use square brackets because usually the task times are in regular parentheses, so to help us distinguish that. Alright, step 2, the backflow algorithm. So once we have the critical time for every vertex in the project diagraph, critical paths are found by following the path along largest critical times. So in other words, the critical path for any task, or vertex X, is obtained by starting with that task and moving to the adjacent vertex with the largest critical time, and from there to the adjacent vertex with the largest critical time again, and you keep repeating that and repeating that. So here's the large example already worked out, and we're going to work out some examples slowly here, but just to kind of illustrate the idea for you. Notice that we start at the end. Here at 0, okay, and the processing time for task FW is 6 hours. So we would say 0 plus these 6 hours creates 6. All right. And then if we were to keep going from there, the processing time for task IC is 1. So it's the critical time 6 plus this processing time, which makes 7. Okay, and from there, PL is 4, so we would take 7 plus that processing time, which makes 11. So PL's critical time is 11. Now, look in the middle. It's a little more tricky when we have vertices that point to multiple vertices. So we'll start from the end again. Task D. Again, we're using critical time 0 plus the processing time is 3. So we would say 0 plus 3, and that gives us the critical time of 3. But then when we look over at HU, this is where it gets weird. task HU has a processing time of 4, and we can obtain the critical time from one of 3 different vertices. So we could look and say, all right, do we want to take it from this critical time of 7 at task IC and say 7 plus 4? Do we want to take the critical time 3 from task PD and say 3 plus 4? Or do we want to take the critical time of EU 2 and add that to 4? That would only be 6. This one, 3 plus 4 would be 7. And this one, 7 plus 4, gives us the 11. So the one we actually choose is the critical time from task IC. So I'm just gonna here, maybe if I highlight that, I'm just gonna highlight that. So that that's the one we chose because it had the highest critical time. There are a few other examples of that in the graph, but let's keep working backwards. So from there, PU only points to EU, so we're going to take 2 plus 3, and that gives us the 5 there. Okay, IP running in kind of to the same situation where we can either take critical time 11 and add 4, or we can take critical time 5 and add 4. We're going to take the 11 and add 4. Oops. Okay. Yeah, we want to have the highest critical time possible. Next, let's look again down at the bottom. So we found the critical time for PU. Critical time for task ID, we're just going to take that 5, add the processing time of 5, and that's where we'll get 10. Up top, task IF, we're going to take critical time of, oh, sorry, this is one that points to multiple ones. So let's figure out this really quick. Task IW points to task IP and task ID. So we could either take 10 and add 7 to make 17, or we could take 15 and add 7 to make 22. And that is the one that we use. So just highlighting here to illustrate that that we would use this particular path because it has a higher critical time. And that's why we get 22 instead of 17. Okay, so now we can go up to IF. IF is another example where we have to choose. We can either take 11 plus 5 to make 16, or we can take 22 plus 5 to make 27. So we're going to go with the higher one there. So that that's the one that we would choose. And at this point, I don't think we have any more of those choices to make. So we have a P, which is 7 hours, so that's incident only to IF, so we'll take the 27, plus 7 is 34. Task AF, 5 hours, we'll take 27 plus 5, so 32. Task AW, we're going to take this 22 here and add 6 to make 28. And then task AD, only incident to task ID, so we'll take 10 and add 8, so 18. That gives us all the critical times for these first round of tasks that are ready when we start the problem. So in the end, we have to figure out the starting critical time, and that's 34, and that comes from taking the critical time from task AP. So if we're talking about critical path, well, really kind of been highlighting it here. The critical path is illustrated. Go back up to AP and then down to start. All right, so highlighted in green here, that really is the critical path for this problem. So now we'll go to a little simpler example. The endpoint, we're going to, in this diagraph, we're going to give that the critical time of 0. Okay, and using that backflow algorithm, we're going to find the critical time for each task. So the critical time for D is only incident to the ending point, so we don't have to make that choice. We can just say 0 plus 2. So D D's critical time is 2. Alright. And actually we're not going to run into that problem except in the end, or at the starting point where we have to choose. The critical time for task A, we're going to take the critical time D, which it's incident to, so 2 is the critical time for D, and we're going to add that to 6, so that makes a critical time of 8. The critical time for B is going to be 2 plus 5, so 7. Alright, down here the critical time for E is going to be 0 plus 5, so 5. Critical time for C is going to be 5 plus 7, so 12. Okay, and at the very end, the starting point, we're going to say the critical time, we're going to look at all the vertices that the starting point is adjacent or incident to, so A, B, and C, and we're going to use the largest critical time, and that largest one is C, so we're going to use that. We'll say 12. So the critical time of the project is 12, maybe hours. Now to schedule this, instead of using the decreasing time algorithm or just choosing a priority list randomly, we're going to use the critical time. So we're going to go down and from largest to smallest in the critical times. And that's basically, this is section 8.5. That's essentially what section 8.6 is, so I'm just going to combine that within this video. That section is called the critical path algorithm, which all we use are the critical times to make the priority list. So the largest critical time looks like it's task C, so that's going to take priority. And to be clear, we're not going to put in the critical time in the list. We're still using the processing time, so that's task C, which takes 7 hours. The task with the next highest critical time is task A, with critical time 8. But again, we're still using the processing time to make our schedule, because that's all the actual amount of time it takes to do the task. Well, sorry, that's kind of sloppy. That says A, and it's 6 hours. Alright, the next highest critical time is task B, a 5-hour task, followed by E, which is a 5-hour task, and then the task with the lowest critical time is task D, and its processing time is also 2 hours. Oops, a different color. Okay, so now we're going to use this list to schedule like we've been scheduling. So we have n equals 2 right here, so we're going to be using 2 processors. So let's look at which tasks are ready. From the starting point, task A, B, and C are ready. So ready, ready, and ready. Go ahead and give task C to that first processor. So that's a 7-hour task. So go all the way up here to 7 hours. Okay, so right now C is in execution. Next is going to be task A. So task A is a 6-hour task. Again, we're still looking at the processing times. We're not using the critical times to make the schedule. We were only using those to create the priority list. So A is 6 hours. Alright, next we have task B, and B is 5 hours. Sorry, let's say that A is in execution. So we only have 2 workers, so look at hour 6 where task A becomes complete. Now we can start task B while C is still being worked on by processor 1. So we'll start task B, and that will take us up to 11 hours. Alright, so task B is in execution. Now at hour 7, task C becomes complete, and we can move on. So once task C is complete, that opens the door for task E, as we see here in and the diagraph where C is incident to task E. So task E is going to take 5 hours. So from 7, we'll go all the way up here to 12. Alright, so currently E is being worked on. Let's look down at worker 2. At hour 11, task B becomes complete. Once A and B are complete, notice on the diagraph, just kind of a review here, A and B are both incident to D. They both need to be complete before we can work on D. So now that they are, task D is ready. So now at hour 11 we can give task D to worker 2. And yeah, starting there at hour 11. So in only 2 hours, so 11 all the way up here to 13. Okay. So, and let's see, it's execution, but then at hour 13 it is finished. And it looks like we're done. So we'll say 13. And in the end, we only just had 1 hour of idle time, so not a bad schedule here. For the last two examples here, I'll at least give you the critical times and ask you to do the scheduling yourself, since we've already practiced that quite a bit. Notice at the ending point, critical time 0. Okay. Looking at task F would take 0 and add the processing time of 6, so its critical time is 6. Going forward on that part of the graph, I'm going to take task D, add the critical time of 6, and processing time of 7, so D's critical time is 13. Task A is incident to task D. We're going to take 13 plus 8, so critical time of 21. Task B is also incident to task D, and so we'd take 13 plus 5, so 18. Okay, let's go down to the other part of the graph. Task G, critical time of 2, 0 plus 2. Task E, we're going to take critical time of 2 from G, add that to the processing time of E, 6, so we'll get 8. The critical time of E, 8, plus 9 for processing time of C, that's going to be 17. Okay, so in the end, our critical time for the project is going to be 21. So now go ahead and use the critical times to make a priority list. So you would definitely want to start with A because it has the highest critical time, and then next would be B, and so on and so forth. So try that, and we'll look over this answer in class. Last one here, ending time, critical time of 0. Let's go up to task E, where we're going to have a critical time of 5. Okay, moving backward from there, we're going to take 5 plus 6, so we'll get a critical time of 11. And moving up to A, we'll take 11 plus 7, so critical time of 18. B is going to have a critical time of 11 plus 4, so 15. Alright, bottom part of the graph. F's critical time will be 7, C's critical time will be 7 plus 8, so 15. Alright, critical time for the project, 18. So again, make a priority list. Obviously, you want to start with A with the highest critical time. And next, you could either choose B or C, but I would choose B since it's pointing to D, which has a higher critical time. So you could do A, B, then C, and then D, so on and so forth. So create that list, create the schedule, and once again, we'll look at that in class and see what you got.